Example 4. Point A, which is at negative AB, which I've drawn in blue, and in quadrant 2 lies on the terminal arm of angle theta. So angle theta is this standard position angle here, theta. And B is the intersection of the same angle with a unit circle. So this red circle is a unit circle, and that has a radius of 1. Okay, so it asks what's the y coordinate of point B in terms of A and B. So I want to know the y positioning on the unit circle. Well, essentially what I'm being asked for is, what is the sign value at that point? Well, to get the sign value, so point B, the y at point B is equal to sine of theta. So all I need to do then is I need to find the length of that hypotenuse of the blue circle. Well, I use Pythagoras to do that. It's going to be a squared plus b squared. And so the position of sine theta, or the ratio sine theta, is going to be b over square root a squared plus b squared. And that represents then the y positioning of point B. So this equality of the y position on the unit circle being the same as sine is very useful, because all this question really is asking is, what is a sine value? So in the unit circle, the tangent value also shows up as a length. Now the tangent value is not inside the circle, it's on the outside. It is this length outside here. And it's called the tangent ratio because the line that is tangent to the circle, that length, as it intersects the terminal arm here, okay, as my terminal arm goes out, it intersects at that point C, and the length of that vertical length is then the tan. And if we think of what tan is slope of sine over cos, or rise over run. Well, that's going to be the same here, because this rise here has a run of the unit circle radius, which is 1. So rise over run is going to be equivalent to rise over a run of 1. Okay, and that's why we get the tan ratio showing up as a length in the unit circle like this. The other ratios, and by the way, if we take a look at that red triangle, another Pythagorean identity then emerges. Since this length here is 1, we can say that 1 squared plus tan squared is equal to that hypotenuse, and that hypotenuse length from here all the way to point C, that actually happens to be the secant length, okay? Because and if we look carefully, it's actually the reciprocal. Instead of doing 1 over cos, okay, so if I draw it in blue here, if I take this blue line, which is 1 divided by cos, well, that ratio is the same as the hypotenuse divided by the adjacent side, or the horizontal side. And so that length must be secant theta. So these other lengths actually do show up in the unit circle. And these are not ones that we use that often. We really should just stick with sine and cos being the horizontal and vertical length in the circle. The tan is useful when it shows up on the outside, okay, but that's less useful. And there's other ones that show up as well. And the cotan ratio shows up as this length here from the horizontal length. And it's kind of equivalent to tan, but it's the horizontal length instead of the vertical length. The cosecant then is the hypotenuse of that triangle, okay, the length from the center to where the cotan meets. And then we talked about the secant and tan. All those ratios actually show up as lengths in the unit circle. So they can be useful. We can use them, but they are a little bit awkward to use. And really, all we really need is a sine and cos lengths in the circle. We can do everything with just those two.